So it's my pleasure to welcome you to the last in this series of Simon lectures. There was a ballot held, and I was afraid I was the only one who voted, or I was happy that I voted. But it seems that I wasn't the only one who voted for the ballot. So it's my pleasure to present Singer, who's going to talk to us about duality.
David even cracked that naturally after S-duality, what could come but T-duality? And Han asked me whether there were any others. Right, exactly. There is something called U-duality. You got to invite me back, and I'll be happy to come. What I want to do today is give a very simple example of T-duality for two reasons. One, it will reinforce what I did with S-duality and abelian gauge theory, where I could actually compute. That's what I'll do today. The other reason is that I frequently, at the end of a lecture, use a lot of buzzwords, whatever the present-day cliches are, and I wanted to have something very concrete and specific to hang those conjectures on, and this simple example will do that. So I'll start with a statement of what I mean by T-duality. One says theory A is T-dual to theory B if A compactified on a space with large volume is T-dual to B compactified on a space with small volume. Now, compactified on means we're thinking of these string theories. These are maps of a loop, or really a moving loop, so a map of a torus or a cylinder into a target space. And compactified on means that instead of mapping into a 9-1 space, Minkowski 9-1, you take one of the real coordinates, space coordinates, and make it into a circle instead. So the statement is that a type 2A string, whatever that means, I'll wave my hand later on, compactified on this space with a circle of radius r. I shouldn't have used r because r stands for Euclidean for the reals, is the same as the type 2 theory compactified on a circle of radius 1 over r. That's what T-duality does. It changes the volume of one into the reciprocal volume. Now, of course, we don't understand what these things are, so I'm just going to erase all this and talk about strings with values in a circle. Just forget about all the rest of the space and show you its relation to strings compactified on a circle of 1 over the radius. In this construction, I will need the Poisson summation formula, and I'll need the special case, which is what happens if you sum over e to the minus c x squared, but for x an integer, to the dual lattice. Well, at any rate, this is a sum. This is a special case of the Poisson summation formula. For any function, we have to use e to the minus x squared, or e to the minus cx squared, where f hat is the Fourier transform of the original function. And also, it's worth noting that this is really a special case that works for any closed subgroup of a locally compact abelian group. Then the integral of a function over the subgroup is the same as the Fourier transform over the character group, G mod H, with the measures, the harm measures, normalized properly. If L is a lattice, the special case of some interest is if L is a lattice in Rn, think of the lattice in a maximal abelian subgroup, subalgebra of semi-simple Lie algebra. What we had called we'd identified with the magnetic charge. Then a big lattice, meaning full so that the quotient is compact. Then this is the dual lattice, which would correspond to the roots in the dual space. And then that sum formula. These f's would be some partition function. You're summing over the magnetic charges. The sectors would be the same as what you'd get in the dual space for summing over the electric charges. That won't concern us here. I really need only the special case of the exponential that I wrote out first. Okay? Now, think about the philosophy that I enunciated in the first lecture. So, you're supposed to replace points in a manifold by loops on the manifold. The simplest manifold that we want to talk about is a circle. So I'm now going to take the exercise of talking about maps of a circle into a circle. The target circle will be of radius r. That's this one. And we're going to talk about, forget this for the moment, we're going to be talking about maps of a circle into this circle of radius r. That's our new manifold. So loops on a circle of radius r will be our new manifold. Set of all such maps is our new manifold. But now I remind you of the Filemancot construction. I really want to talk on this new manifold. I want to talk about the Laplacian plus potential function, and I want to talk about its eigenvalues, but it's very hard to get at directly. We could. The best thing to do is look at the heat kernel for that operator, and out of that we can get more information than as much in Laplacian, or I should say the Schrödinger operator, has instead. So the philosophy, or part of what I'm trying to do is for mathematicians, that there is a consistent theory here. There's a consistent story. And so what may seem unnatural is really actually very natural. So we really want to study the Laplacian plus a potential function, which is the length squared of the vector field, the derivative along a curve. We want to talk about that Schrödinger operator. We want to study its eigenvalues on an appropriate Hilbert space. But it turns out that a good way of studying it is to talk about the heat kernel for that operator. And then a good way of studying that is to remember the Filemancot's formula, so that what we want to do is talk about the Filemancot's formula for the heat kernel and for its space. So you end up talking about maps of a circle of length t, radius t over 2 pi, with values in this space of maps of a circle into R, and that's how I come to this space of maps into a circle. This represents the loops in it, and this is represent the loops evolving in time and coming back on itself, the closed loops in that space. And it takes period t to come back. So we are talking about then these two ideas of replacing the points by maps of S1 into a circle of radius r, and then we want to find the trace of e to the minus 2 pi t of this Schrödinger operator via Filemancot's. This would be the partition function ztr and alpha I'll describe in a moment for that space. So we want to compute it, and that'll give us information about the eigenvalues. Well, I write down the action with a coupling constant alpha prime in front for such maps. And I briefly alluded to this in the first lecture. That action really is the Filemancot's formula for the heat kernel for this operator, if it existed. In fact, in this case, it does exist, but we won't worry about it. It exists because of what you'll see, that we can actually make the computation. So that's the action, and we can compute it because, of course, we can break up this big space into its components, and the components being given by two integers, the winding numbers of these two circles around S1 of R. And in fact, if you have something in chi of Mn, it can be represented by a winding number M and N by these explicit maps times R, which is the radius of the target, and the part that's homotopically trivial once you've got this piece, which you can write as an exponential. That is, that part would have a logarithm. So the f's are just functions of this torus, functions on the torus. You're taking the exponential. With M and N 0, we're simply talking about those maps with winding number 0, and those have logarithms, both winding number 0. Now you compute. You can compute what's on the first line, and you can see what we're going to get as the action. And what you end up getting is this expression, where df squared means the differential of the function all squared, integrated. That's what partial of phi with respect to x squared, the second derivative, plus the Laplacian on f integrated is going to give. So this is what you get. So we can write this as pi r squared over alpha prime times the Laplacian of f inner product f plus this expression when phi is in the Mn component. It's a simple computation to get that far. So that tells you what the action is, and now the partition function, that is what's supposed to be the trace of e to the minus t times the Schrödinger operator, is integrating over all such fields phi in this space chi, weighted by that action. Note, by the way, if you looked on the previous page, r and alpha prime weren't, they occurred in this ratio, actually, in the two. So now we want to integrate this, and this is supposed to be the trace of e to the minus t Schrödinger for a circle of radius really r over the square root of alpha prime. So I now want to compute. It's quite straightforward. We're going to integrate over all phi. Well, they break up in the components, m and n. And then you're going to integrate phi over components. And we write it out, and this is what we get. We'll get a piece which is common to everything. That is the homotopically trivial component. And the rest, we get a sum over Mn of this expression. Now let me stop here for a moment to emphasize the similarity with what we did in the case of S-duality for abelian gauge theories. Remember, I deliberately, in fact, wrote it in a way where you got a piece that only depended on the trivial line bundle, and then that was a common factor, and then the rest was a sum over C1, and that was the part that really gave you a modular function with some problems about the metric that you had to solve because of the common factor. The same thing is happening here. We have a term, this part, that means this part right here, Z0 stands for the trivial component, which is common to everything, and then we have the rest, which is a sum over the different components that's just picked representatives, just like we picked harmonic representatives in the case of abelian gauge theory. And even in this part, we're going to break it up into two parts. One is the sum where the t is in the numerator, and the other is the sum where the t is in the denominator. The n, remember, represents, forgotten which order, I guess the m represented the actual winding of the space loop around the target, and the n represented the winding of the time circle of period 2 pi t around the target. Now, this one I'm happy about. Remember, I'm supposed to be computing the trace of e to the minus t times the Schrödinger operator. We expect to get eigenvalues, so you should get t times eigenvalues. We expect to get that thing to look like e to the minus t lambda n for the eigenvalues, if you ordered them, sum over n. It should look like something like that. The t should be here, right? This part's fine. Here, a t is in the denominator. Now I remind you, now you see why I started off by writing down the Poisson summation formula. In that, I should have emphasized that what you do, of course, is the coefficient c in there got changed to its reciprocal. In fact, I ought to emphasize that more. Let me go back to that example if I can find it. Oh well. In this case, if you use the Poisson summation formula, then this sum is equal to this sum. Now I'm happy. I got the t in the numerator, and I can think of this as eigenvalues. Okay? So we end up with seeing that this partition function, I should emphasize partition function is only one piece of the quantum field theory, but in this particular case, the most interesting piece, is written as the part that comes from the homotopically trivial part, which we haven't analyzed yet, times this term, e to the minus pi t, and here we have this term, which should be part of the eigenvalues that we're getting. Now we make the remark, and this is what T-Duality says. If r tilde is alpha prime over r, then this expression is the same as the expression if you just substitute for r. You get the same expression except m and n are switched. That's already interesting because n and m play different roles. You could think of one of them, the space circle wrapping in, as a monopole number. That's topology. And the other, I don't know what to say. It's not electric charge, but two different topological things get switched by changing r into 1 over r. It's like the switching between magnetic and electric that I was trying to describe. I feel unsuccessfully last time, but at any rate, I was trying to describe. Now, if we can show that this term is independent of r and alpha prime, then we will see that the partition function based on r and alpha prime will be the same as the partition function where the target radius is alpha prime over r, and actually this is the same as et 1 over r, but you change the coupling constant to 1 over alpha prime. That's what T-duality means in this baby example, infant example actually, that you get the same partition function. Actually you want that the whole quantum field theory is the same, but we're only doing something we can compute directly. It says that the partition function based on the target circle of radius r is the same as the partition function if you based your target circle on radius alpha prime over r. That's what I meant about when you compactify. We've compactified on a circle only, that's all we got, that the volume switches to 1 over the volume. Okay, so all that remains is to show that this is independent of r and alpha prime. And now we're in the same position again that we were in the case of abelian S-duality. We got an integral, a functional integral that is Gaussian, and now it's just got to be the right interpretation or regularization or definition or what have you about what you mean by Gaussian integrals. A little exercise I went through then, and I'm going to go through now. Okay, well, we want to integrate over, this is the expression we're going to integrate. Here's our Gaussian, here's our quadratic term, and we're going to integrate over all functions like this. One of the problems here is that there are functions which are killed by the Laplacian, namely the constants. So we want to factor those out. We can write this space we're integrating over as a product, those which are constant maps and those for which the integral over the circle is 0, over the torus is 0. Now, integrating over the constant maps, this is the same as r, would just get 2 pi r. So I'm making a definition that if I have the circle, the volume I'm talking about there is the ordinary volume, 2 pi r. The rest is the integral over these with f equal to 0. Now we're going to write this in terms of, because we got the exponential map, I don't really know whether it's worth carrying all this out. I'm just doing some formal things and saying that's what I mean by the integral. We really have a map which sends f into this expression, and we want to replace d phi by df, so we need the Jacobian of the map. We compute what the Jacobian is. It's constant no matter where you are for what f, and what you get is 2 pi r times the identity map. We want to get the determinant of that. Of 2 pi r, I remind you, you're going to get it. So we have the 2 pi r that came from this term. I'm looking at this expression. We got the 2 pi r over here. Then we've got the determinant of this times the identity. Remember, our convention is it's 2 pi r raised to the dimension of the vector space. It's true the vector space is infinite dimensional. We've regulated it last time. We're going to regulate it the same way. So it's going to be 2 pi r times the dimension of what? Now the functions are those with integral 0 or the orthogonal complement of the constant functions. And then what's left is the integral of this box means the Laplacian, but only on functions orthogonal to 1. So that there's no 0 in here. This integral makes perfectly good sense. That is in the conventions I've used. So here's a quadratic integral. We know that this quadratic Gaussian integral, we know this means 1 over the square root of the determinant for this expression. So we end up with 2 pi r to the dimension of 1 perp, the 1 over the square root of the determinant of this operator. Then we use the device we had before, that we can factor this out. If we had determinant, this would be factored out by the dimension of the space. Now we have the square root minus the square root, so you'll end up with this expression for the partition function we want. Well, you see, these r's are going to cancel, even if we don't know what determinant. Without whatever regulation you're going to use, that part's going to cancel. This part doesn't depend on anything but the torus that we talked about, namely a torus, a square torus with a t and a 1, not the target in any way. And here's what we have left. We put all that together. We can actually compute what the dimension of one perp is. It's this operator to the minus s at s equals 0. I remind you, heat kernel expansions. Well, I don't want to go into that technology. It turns out to be minus 1, so you end up with this expression looking like that. And so finally, the part that we wanted to be independent of r and alpha prime is the expression here. And it is independent of alpha prime and r. So the final formula for ZTR alpha prime is this one. Okay, so I've really shown what I wanted to show you, although I'm going to say another word or two about it. Namely, I've shown you that that partition function does what it should do if you replace r by alpha prime over r. You get the same partition function, and that is a reflection that these two quantum field theories are the same, at least at the level of computing the partition function. And it's not a completely trivial theory. If we were mapping into the reals, then it's a free theory. That's the part Z0. But we're mapping into a circle, and there's a little bit of topology that you have to take into account, which you do by the Poisson summation formula. That's really what I did. Okay? Now there's one thing that's remaining here. If you look at this formula, this is supposed to be the trace of a heat kernel. It should be the whole thing should look like that. Whereas what I've got is only this part looking like that. And I've got this other factor in here which comes from the homotopically trivial piece. It also should look like this. Okay? Well, I don't want to go into that. I've illustrated my point. Something like the following. You can compute this determinant on a torus. Ray and I did this when we studied holomorphic torsion years ago. And for tori, it comes down to the Dedekind second limit formula and involves the theta function, which you can write as a product. You write that product out, and then we're taking 1 over the square root of a product. And when you write that out, you're going to get things of the form 1 minus e to the minus k something in the denominator, which you'll write as a sum. And if you put all that together, you will be able to write formally this infinite product as things of this type. So you could actually write it out and see what the contribution of the free field theory gives you. That is the homotopically trivial stuff. And then you have to check that it really does correspond to the right eigenvalues for the Schrödinger operator for the free theory. And those of you who have been studying Fock spaces should know that what you do in these matters is you just look at the one-dimensional Fock space, You look at the operator there, and then it extends as a derivation on the symmetric products. So once you know the eigenvalues on the first Hilbert space, you can get them as symmetric products, and you write all that out, and that's what you get as the Gaussian, as this determinant. So I won't carry that out, but it's a nice exercise for those of you who are studying free field theory to actually do this in the case at hand.
Why is the square root of t work? Yes, I understand the theta function argument.
Yeah.
I understand the expansion. But you still, that square root of t is not in the theta function.
No, but the actual value involves the scale as well. I mean, the value of the determinant in the second limit formula will take care of that. Okay. Now, as I told you at the beginning, I was going to do an explicit concrete, and now I'm going to start waving my hands and using buzzwords, okay? So the mathematics lecture is over. There are 5 types of superstrings in R91. The closed strings of type 2A and type 2B. We were pretty close to those closed strings when at the end of my first lecture I stringified the supersymmetric quantum mechanics, and I wrote down an appropriate Lagrangian. Peter reminded me that that's called a spinning string. That was a type 2 string. And what do I mean by type 2A and type 2B? Again, I want to emphasize that what one is doing is there's supposed to be concrete operators out there that you're trying to find the Filemancot's integral formula for. The operator of great interest in this case is the analog of the Dirac operator for a manifold. You want the corresponding Dirac operator plus, since you're talking about strings, so strictly speaking, we would be looking at loops on a manifold. Luckily, this manifold here is R91. And then we would like to talk about the Dirac operator plus a potential term, which is Clifford multiplication by the vector field that's natural on this space, the tangent vector to the loop. That's the Dirac-Ramond operator. Purely formal if you had a curved manifold. But when you have R91, it's flat, and you have a whole technology of oscillators, annihilation, creation operators, etc., in which you can really make sense of this operator. Now, the difference between type 2A and type 2B strings is this. A type 2A string, non-chiral, means you really want to look at the Hilbert space that would be all the spinors, both plus and minus, chiral, positive chirality, negative chirality spinors. You want to look at that full theory. In the type 2B string, you only want to look at those that go from positive to negative spinors. But that's kind of half of the previous one, so you do it twice, plus to minus twice. And you're looking at the Hilbert space of the appropriate of that for those two appropriate operators, and those are called the closed strings of type 2A and type 2B. It's kind of a miracle from what I'm saying that they're both n equal 2 supersymmetric. That is, they're two supersymmetries of the Lagrangian for that theory. There's a reason I'm going through this, which I'll explain shortly. Then the third type is an open string. These are maps not of a closed of a circle, but of an interval into the manifold. And Chan-Paton factors means that the manifold has a vector bundle on it, and you don't just have a map of the open string n, but you've chosen a vector in the vector bundle at the initial point, image of the initial point, and a vector at the bundle, the end point. So it looks like this with appropriate action. Here's your open string. You've got a vector bundle, so you've chosen a vector here and you've chosen a vector there. Then there are two heterotic strings, they're called. Heterosis meaning a melding of two different things. And again, I'll only use some buzzwords, but I want to come back to those buzzwords in a minute. What happens in this theory is, because you're mapping a torus in, or at least a two-dimensional object in that has complex structure, and you're in a flat space, so you can really separate out, the Hilbert space is split into holomorphic and anti-holomorphic. It's really, the metric on the torus is of type 1-1, so you can talk about x plus t and x minus t, and these two fields move in these two different directions. The heterotic string takes what you normally do with a left-handed part, and it does something different with a right-handed part. What it does different on the right-hand part goes back to the affine Lie algebras, Kac-Moody construction for an affine Lie algebra. And so there you're talking about strings with values in a group. For the moment, could be any arbitrary group. That gives you a very nice right-moving field theory, and you merge the two together. Turns out, by what for us right now would be miracles, the only two groups that are allowable is rank 16, E8 cross E8, so 32. Now, the excitement, being more specific now about the excitement in the last couple of years, is that all these strings are kind of dual to each other. They are really related. And what's interesting is this fact, that in 3, you see the Lie algebra. You see you have a vector bundle. That means you've got the group of the bundle at the end, so it's there explicitly. In the heterotic strings, you see the Lie algebra. That's the way it was built. It was built out of the affine Lie algebra construction, and there is this group. But in these closed strings, you don't see them at all. So the interesting thing is, where is the Lie group coming from? Before I do that, I should also say that there are low energy limits. Where is it? These string theories have low energy limits. You want to see what happens as the strings collapse to a point. In the type 2A, you get non-chiral supergravity. Peter, one of the discoverers of supergravity. In type 2B, you get chiral supergravity in 10 dimensions. For all the other cases, you get supersymmetric Yang-Mills based on either SO32 or E8 cross E8. Okay, now I'm going to tell you some of the, so you get a feeling for some of the dualities. Okay? I'm repeating what I started this lecture with, which was that closed strings of type 2A compactified on one circle. That means that the target space is no longer R91, but I've replaced one of the Euclidean coordinates by this circle, is T-dual in type 2B compactified on this other. Now you should feel, well, maybe that's not so surprising because I just carried out in some detail, forgetting about the rest of the space, right? That's what I did. There's a whole construct of, as I say, of string theory on a Minkowski space that I've just forgotten about, simply because by and large the audience doesn't have the background to deal with it. But you can begin to ask questions, you see, even now. You can say, well, whatever the string theory is, here's an example of what you could just check directly. I should emphasize in this case of 1, you really can ask whether that's true or not, because everything makes very good sense. The part with the circles I showed you how to do, it's almost free. You break it up into components. The parts that's not the circle is a Minkowski space, and you have the annihilation, creation, three-Fock-based technology to handle it. But you see, you could ask questions like, well, if we look in the type 2A string for R91, then we have SO91 acting on that space. Let's look at the part of the vector space that's massless, that the vectors in there have mass 0. Let's look at the representation of SO91 you're going to get there. You'll find that in type 2A and type 2B, they're not the same representation. On the other hand, if you compactify on these circles and you reduce to SO81, so just restrict to SO81 on the massless sector, lo and behold, the two representations are the same. That's a statement about representations that you can check in this case, known before the duality, and that's a reflection of this duality between these two types of string theory. So I've given you the simplest example of duality, which at least you should resonate to, having gone through the exercise of the first part of the lecture. Now we get to something really sophisticated. It's conjectured that type 2A compactified on the Calabi-Yau. That means the target, since the Calabi-Yau is real 6-dimensional, what's left is R31, so that this is S-dual to a type 2B on the Calabi-Yau mirror. Now that is only a conjecture because we can't really say what these field theories mean. Martin's sort of shaking his head. As a mathematician, I don't know what they mean. I was about to say, here's a conjecture which you can check out in various ways. You would check what the moduli space of vacua look like for these two theories. You would check what the quantum space of vacua look like for these two theories. You might check what the low energy limit looks like for two theories. You could check various things that come out from this conjecture to see whether it's true or not. So far, all checks say yes. And they're dramatic. It's not, these are not trivial statements. Well, I think the name of the game right now is you've got a lot of conformal field theories here. You really want conformal theories in which SO something acts. So that's what you really want, is physically. You could make these conjectures mathematically in various cases, but physically what you want is a conformal field theory in which there is a symmetry due to SO_K1. And in fact, that's one of the exciting things, is that these deep branes with values in something are new conformal field theories which have the symmetry of some SO group. Now I'm just listing some statements which physicists were surprised by and delighted by because they really only want one string theory. Pardon?
Your conjecture 2. You say that the 2A theory compactified on the S2. You mean S2?
Yes, not T, but S. But there recent developments, say, since I've been here, that I haven't had a chance to look at, which Vafa and collaborators claim that you can forget S-duality and everything is going to come out of T-duality. I don't know what that means, actually. But that's what I read from, what I understand from the first page. Now I want to make one other comment here where you can begin to see that you could actually make a lot of computations, and that is, rather than compactify on in a Calabi-Yau, we compactified on the circle. But now suppose you took a torus. The same kind of procedures I described working on a torus is similar to what I did for a circle, so you could actually compute and see what the moduli spaces look like, and it's kind of surprising that in fact you find what might appear to be different kind of moduli spaces are the same in cases where you can actually make the computation. Well, 4 and 5 I just listed for some kind of completeness, so you get a flavor for them. It's 6 that I want to talk about for a moment. And here's what it says. Once you decide that you want to look at T-duality, it says if you look at the open bosonic string, so there's no supersymmetry, you're just looking at maps of an interval into a target space, which is R24-1. Now the dimension of the space, because you're not dealing with supersymmetries, should be 26. It's R24-1 with a circle is T-dual to open string with target space this circle in R24-1, but with the endpoints of the string lying in R24-0. From what I did, you should be able to do that as an exercise, actually. And by R24-0, I mean the complement to the circle in this space. Take a point in the circle, and that's called a Dirichlet brane. This submanifold is called a Dirichlet brane, meaning Dirichlet boundary conditions. And you do get, to emphasize Silvati's question, the new recognition is that talking about open strings with values in a submanifold that is in the space part gives you a new conformal field theory where an orthogonal group will act. And more than that, what it does for you is give you some new topology so that you got set theory above and beyond what you had before. What you'll have are forms which you can integrate over normal spheres to the submanifold, and that's going to give you, what those numbers are going to be, is going to give you new sectors. And that turns out to tell you or explain why some string theories are dual to another. A string theory that has components, when you dualize, you've got to see them in the other theory. So it does, T-branes do several things for you. even though they've been around for a bit, Joe Polchinski's been talking about it for a long time. It's only in the last couple of years that one realized their importance. So I repeat the definition. And I've just briefly alluded to why they're important. Now the question I raised earlier, the type 2 strings don't exhibit the gauge group, but the other strings do. How do you construct the gauge group? Well, we can't do it here. We just don't have the machinery. So what I'm about to say is an advertisement for Martin Roczek. And this is an introductory lecture to his explaining to mathematicians over the next year how to do that. The critical thing is, remember, we took this into the reciprocal. When these two are equal, then you can show, and Martin showed me in a very neat way, that in fact, you see, we were talking about maps of a circle into a circle. That would be a certain part of the affine Lie group for SU2, with the circle being the maximal torus. You can actually fill that out to get the two other representatives of the Lie algebra, or I should say elements of the Lie algebra. We've got the circle, so we've got its infinitesimal generator, H, and then we would have x plus and x minus for the other two things. You can actually construct them out of this quantum field theory. Martin showed me how to do it using conformal field theory in an elementary way, but we don't have that available to us. I actually spent all night, Martin, trying to eliminate conformal field theory and make your construction direct and see if it was simpler than the one I know. And I came away this morning deciding that conformal field theory. I knew that before, but this time it really hit home. So I can't make that construction for you, but in fact, I bring to your attention that even in the construction of the representation or the fundamental representation of affine Lie algebra, there is a very nice paper by Frankel and Katz, which makes algebraic what is the physics construction. And they show you, if you start with maps of a circle into a circle, look at the plus knowing the roots for the circle into a torus, it's the maximal torus, that's all you've got, plus the roots, the Dinkin diagram. You can, out of that, find not only the rest of the Lie algebra, but the affine Lie algebra as operators on the appropriate Hilbert space. That is what enters in the heterotic string, that out of maps of a circle into a torus, you can construct the whole thing. But the construction really comes out of vertex operators, which is part and parcel of this whole development. So you can, in principle, reproduce by knowing only maps, only strings with values in the maximal torus. Now that's really very interesting. So you get the answer to the question, how do you construct a gauge group in these simple cases, by one way or another, I'll call it the Frankel-Katz construction, but it's really the vertex operator construction in quantum field theory. Actually, there's more to the story, and perhaps for me, the most exciting part, and that is that one is beginning to see, or at least physicists are beginning to see, that in these type 2 strings, especially with compactified and the Calabi-Yau, you can flesh out the ADE classification of singularities by actually getting the ADE groups. This is just coming into consciousness for mathematicians. But the idea is that you look at one of these type 2 strings compactified in the Calabi-Yau. There's a whole family of them due to the moduli space of Calabi-Yaus. And you see what happens as you approach certain singularities in the Calabi-Yau in very special cases where spheres collapse to points, and that singular point can be described as an ADE classification. And in the spirit of what I've just said, the volumes of these spheres that are being collapsed to a point, the volumes are proportional to the masses of corresponding elements in the Hilbert vectors in the Hilbert space, fields in the Hilbert space. Those masses go to 0 as you collapse the spheres, and so you're getting spin 1 vectors or fields which are massless, and they begin to give you the corresponding Lie algebra, and in fact you can actually construct the Lie algebra of this Dynkin diagram from the quantum field theory. So that should be very interesting for mathematicians to see that carried out in some detail. But certainly it makes the recent developments in string theory exciting. The first reason was that you saw the quantization of gravity, meaning that you saw spin 2 massless particles. Now we're seeing spin 1 massless particles and actually gauge theories emerging out of type 2 strings when they're not just sitting there. You're not handed them. Okay. I had a prologue when I first started these lectures, so I think symmetry insists that there be an epilogue as well. Now, let me say a few words to this. The reason I gave these lectures and stuck to elementary things, well, I stuck to elementary things. That's the only thing I know, the elementary aspects of the theory. But the reason I gave them was to alert young people that the interface between math and physics these days is very exciting. And I think here, with the background of people in physics and the background of people in mathematics, is a wonderful occasion to learn both. That's why I entitled my lectures as String Theory and Mathematics. My own motivation is, it's just interesting. I just find this very interesting. There's a deeper motivation. There are connections between math and physics. They have a common feature of symmetry and geometry. And it could well be that what one is looking for, M theory, F theory, there are various names for some way of looking at this entire subject of these different string theories as a consistent one real theory. It could well be that what lies behind it is just as likely mathematical as physical, and I think it's important for young people to be comfortable with both subjects, even though it takes a long time. But I think there's something very deep going on, and it is some combination of mathematics and physics, and be interesting to see how that develops. Of course, the third reason for most mathematicians is that they provide technical assistance. I mean, you want to know how a K3 can be fibered by tori, or how a Calabi-Yau will be fibered by tori with singularities. I might say, I should have said this when I talked about T-Duality. I emphasize the circle because somehow in T-Duality there's always a circle. Might be a product of circles, but there's always a circle. And if only everything were fibered by circles or tori, then the theory would be very simple. It's because there are singularities in the fibration that life gets difficult and there's a lot of interesting technical problems for mathematicians to get involved in. And of course, the fourth reason is new mathematics. This stuff is generating new mathematics. I think it's quite likely we'll see some new applications of four manifolds by some of these quantum field theories. In fact, to startle you a bit, I think the Donaldson theory was really a remarkable revolution in saying something you wouldn't expect, that if you look at the moduli space of self-dual solutions to Yang-Mills, out of it you're going to build a manifold invariant. That's remarkable. So remarkable that people in four manifolds keep, frankly, doing the same thing. If it's not Donaldson theory, then now it's Seiberg-Witten theory. You still, what do? You still look at the classical solutions, that's a moduli space, and you're going to do things with that moduli space. There's still vanishing theorems and counting, etc., integrating over the moduli space. But if there's anything one has learned here, is there's much more to the quantum field theory than just the moduli space. There might be aspects of the quantum field theory that also have a lot of topological information above and beyond the classical moduli space. There's quantum moduli space. There's more to the field theory that might, so that what we have been doing since Donaldson showed us the way in 83 or 84, what we've been doing is looking only at the classical moduli space and nothing more. There's a lot more going on there that ought to be looked at. And a lot of different mathematics, which I've listed here. Thank you. Thanks, Blaine. It's my pleasure to have such an attentive audience.